Hi friends, welcome to the lecture of Advanced Discrete Mathematics. In last lecture, we have seen what are the permutations. Now we have to see some particular types of permutation. First one is restricted permutation. The number of permutations of n different objects taken are at a time in which k particular objects do not occur is nothing but the permutation of n minus k things where r will be taken at a time, which is nothing but here we have to take the number of permutations of n different objects taken r at a time in which these k particular objects do not occur in that arrangement. So here we have to take the permutation of n minus k things where we have to take this r at a time. In second one, the number of permutations of n different objects taken r at a time in which k particular objects are always present. That is, here out of these n different objects, k objects are always present in the permutation, which is nothing but the these are the r objects that we have to take, and k are always present. So here we have to take the permutation of r r different objects where k will be taken always, and remaining is nothing but the permutation of n minus k things where r minus k taken at a time. Okay, so which is nothing but the number of permutation of n different objects taken r at a time in which these k particular objects are always present is nothing but the permutation of n minus k things where r minus k will be taken at a time into permutation of r things in which k will be taken at a time. Okay, now we have to see the example depending on these 2 points. Okay, let in how many of the permutation of 10 things where 4 will be taken at a time, then we have to check for the 2 things always occur and 2 things never occur. Now here we have to first see the 2 things always occur. So keeping aside the 2 particular things which will always occur, that is the number of permutations of 10 minus 2, which is nothing but the 8, and taken 2 at a time is nothing but the permutation of 8 things where 2 will be taken all time. That is 2 things always occur, which is nothing but the 8p2. And now 2 particular things can take up any one of the 4 places, since here we have to take 4 places at a time, and as always 2 things are always occur, then these 2 things take any one of these 4 places, and so they can be arranged in 4p2 ways. So the total number of permutation is nothing but the 8p2 into 4p2, and which is equal to 672. Okay, so the number of permutation of 10 things where 4 will be taken at a time in which 2 things always occur is nothing but the 672. And in second one, 2 things never occur. Therefore, leaving aside these 2 particular things which will never occur is nothing but the number of permutation of 8 things, since 2 are never present in this permutation. So the permutation of 8 things were taken 4 at a time, which is nothing but 8p4, and which is nothing but the 1680, that is 1680. So the next example is, in how many ways can 7 boys and 5 girls be seated in a row so that no 2 girls may sit together? Okay, as here given that there are 7 boys and 5 girls, and there is no restriction on these 7 boys. Let us suppose the position of these 7 boys is nothing but b1, b2, b3, b4, b5, b6, and b7. Now we have to take these 5 girls and we have to sit these 5 girls in these star places. That is, here we have to take a 5 girls be seated in a row so that no 2 girls may be sit together. So as here there is no restriction on 7 boys, then these 7 boys can be arranged in 7 factorial ways. Now if 5 girls sit at places indicated by this symbol, that is take either here or here, okay, then no 2 of the 5 girls will sit together. If we take the position of these girls as this one, then there are no girls sit together. Okay, now clearly these 5 girls can be seated in these 8 places: 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and now these 8 places, here we have to get 5 girls can be seated in 8 places in 8p5 ways, which is from the definition of permutation. Okay, now hence the required number of ways of sitting 7 boys and 5 girls under the given condition, which is nothing but 8p5 into 7 factorial, and which is from the product rule. Okay, in this way, the 7 boys and 5 girls be seated in a row so that no two girls may be sit together. Then the number of ways are nothing but 8p5 into 7 factorial. Now, next example is, in how many ways 4 boys and 4 girls can be seated in a row so that boys and girls are alternate. That is, then there are two possibilities for it: when a boy is sit at the first place, and second possibility is when a girl is sits at the first place. Let us take boy sits at the first place. Then the possible arrangement will be of the for first one we have to take boys, second one girl, again third one is boys, and fourth one is girl, and continuous in this way we have to take 4 boys and 4 girls, and which are alternate. Okay, now there are, as there are 4 boys, then these 4 boys places can be seated in 4 factorial ways. That is, now there are as 4 places and 4 boys, therefore 4 boys can be seated in 4 factorial ways. Again there are 4 places for each girl, that is 4 girls, therefore 4 girls can be seated in 4 factorial ways. Hence the number of ways in this case is 4 factorial into 4 factorial. Since there are 4 factorial ways for the boys and 4 factorial ways for the girls, then by the product rule there are 4 factorial into 4 factorial ways for both boys and girl. Now, in second condition, we have to take the girls are sits at the first place. Then the possible argument will be of the form girl, boy, and so on. Okay. Then, according to this case one, the number of argument are again 4 factorial into 4 factorial. Then, such a possibility of sitting the 4 boys and 4 girls in which no boys and girls are alternate is nothing but 4 factorial into 4 factorial plus 4 factorial into 4 factorial, and which is from the sum rule of the combinatorics. Okay, now the next thing is permutation of things not all different. Okay, so let us take to find the number of ways in which n things may be arranged among themselves, taking all of them at a time. When p of the things are allowed, as here there are given that n things are present, in which p things are alike of one kind, and q of them are alike of second kind, and r of them of a third kind, and the rest are different. Okay, there are n things in which p things are of one kind, q things are of second kind, and r things are of third kind, and all the rest things are the different. Now let us suppose x be the required number of permutation, which is the x is nothing but the number of permutation of n things where all of them taken at a time, or okay. Now replace these p alike things by p distinct things which are also different from the remaining n minus p things. Here we have to replace p alike things by p distinct things which are also different from remaining n minus p things. Now these p different things may be permuted among themselves in p factorial ways without changing the position of other things. Okay, now thus if p alike things of one kind are replaced by p different things, then the number of permutation by the product rule are nothing but x into p factorial. X is the already the required number of permutation, and these p factorial are nothing but the permutation of these new p things. Therefore, the number of permutation will be equal to x plus p factorial. Now, if any one of the x plus p factorial permutations we replace q alike things. Now we have first replaced the p alike things. Now we have to replace these q alike things, okay, of the other kind by q other different things, and again then the number of permutation of these q new things which are different among themselves without disturbing the arrangements of rest will be nothing but the q factorial. Since these q things are different, therefore these q things are arranged among themselves in q factorial ways. Okay, Now thus if both the replacements are done, that is p alike things and q alike things are replaced, then the number of permutations are nothing but the x into p factorial into q factorial. Now similarly we have to replace these r alike things by r different things. Then the number of permutations are nothing but the x cross p factorial into q factorial into r factorial. Now each of these x cross p factorial into cross q factorial into cross r factorial permutation is a permutation of n different things taken all at a time. Since we know that if we have given n things, then they are arranged among themselves in n factorial ways, and these are nothing but x cross p factorial cross q factorial cross r factorial is nothing but the n factorial, and from this x is nothing but n upon p factorial into q factorial into r factorial. That is, here we have to divide this n factorial by p factorial into q factorial into r factorial. Since these p things are alike of one kind, these q things are also of second kind, and these r are of third kind. So here we have to remove this part from this n factorial. Hence x is nothing but the n factorial upon p factorial into q factorial into r factorial. Now let us see the examples of this point. Now how many permutations of the letters of the word banana? Okay, now there are 6 letters in the word banana, of which 3 are alike of one kind, that is there are 3 a's in this word, and 2 are alike of second kind, that is there are 2 n's in this word banana, and rest one letter is different, which is a b. Now according to the above point, this x is nothing but n factorial upon p factorial into q factorial into r factorial. As there are 6 letters, then n is nothing but 6. Let us take this p as a and q as a p is nothing but 3 according to this word banana, since there are 3 a's in this word, and q is nothing but 2 since there are 2 n present in this word, and which is nothing but the required number of permutation are nothing but 6 factorial upon 3 factorial into 2 factorial. 3 is nothing but the p and 2 is nothing but the q. Okay, and 6 factorial upon 3 factorial into 2 factorial is nothing but 60. Okay, now second example is, if a coin is tossed 6 times, in how many ways can we obtain 4 heads and 2 tails? Now its solution is nothing but whether we toss a 6 coin 6 times, or sorry, whether we toss a coin 6 times or toss 6 coins at a time, then the number of arrangements will be same. Okay, then the number of arrangement of 4 heads and 2 tails out of 6 is nothing but this 4 is nothing but p and this 2 is nothing but q, and which as there are 6 coins, therefore, or we can toss the coin 6 times, then this n is nothing but 6, therefore the required number of, that is how the number of ways that we get 4 heads and 2 tails is nothing but 6 factorial upon 4 factorial into 2 factorial, which is nothing but the 15. Now we have to see the next point. Now we have to see the permutation of things with repetition allowed. Okay. Now the number of permutation of n different things taken are at a time when things may be repeated any number of times is n raised to r. That is we have to prove. Let us suppose there are r places and we have to fill these places with these n things. Then the first place can be filled up in n ways, since there are n possibilities for the first place. As here we have to find out the permutation with repetition allowed, then the second place has also n possibilities. That is, the first place can be filled up in n ways, and when it has been filled up in any one of these ways, the second place can also be filled up in n ways. For the thing occupying the first place may occupy the second place also, since here we have allowed the repetition. Okay, thus the first 2 places can be filled in n into n, which is equal to n square ways, which is from the product rule. Okay, now when first 2 places can be filled in when the 2 places are filled in any of the n square ways, the third place can also be filled up in n ways, since here we have already allowed the repetition, and so the 3 places together can be filled up in n square into n, which is nothing but the n cube. There are n cube ways for the first 3 places, and proceeding in this way, we conclude that these r places can be filled up in n into up to so on r times, and which is nothing but n to the power r ways, n to the power r. Therefore the number of possibilities, that is number of ways for filling these r blank places with n things with repetition allowed, is nothing but the n to the power r. Let us see two examples depending on this point. How many number of three digits can be formed with the digits 2, 4, 6, and 8 when a digit may be repeated any number of times? Here we have to find the number of three digits which can be formed with the digits by using these four digits 2, 4, 6, and 8, and we can take any digit in number of times. As there are three digits, first digit have four possibilities, second digit also have four possibilities, and third digit also have four possibilities. Therefore the solution is nothing but, since repetition is allowed, each of these three places in a three digit numbers can be filled up in four ways by the given four digit. That is, the 100 place has four possibilities, 10th place has also four possibilities, and unit place also has four ways. Therefore the required number of three digit number is nothing but 4 into 4 into 4, which is nothing but 4 cube, and 4 cube is nothing but the 64. Now second one is, in how many ways three prizes can be distributed among four boys when a single boy can get any number of prizes? Each of the three prizes can be given in four ways, since a boy can receive any number of prizes. Therefore first prize have four possibilities, it can be given any among these four boys. Similarly second and third prize also have four possibilities. Therefore the number of ways in which all the prizes can be given is nothing but 4 into 4 into 4, and which is the 4 cube, and which is again 64. Now the next point, which is a circular permutation. We have already seen some types of permutation, which are restricted permutation, permutation of things which are not recurrent when repetition allowed. These permutations are nothing but the linear permutation. But now we have to see what is the circular permutation. Let us see before that the permutation that has been described above are more properly called as linear permutation, as the objects are being arranged in a line or in a row. Now, if we arrange them in a circle, then the number of permutation changes. A circular permutation is an arrangement of objects around a circle. Okay. Now consider four persons A, B, C, and D who are to be arranged around a circle. The following arrangements are one and the same as relative position of none of the four position A, B, C, D is changed. That is, these four permutations are same since there is a cycle. Here also A, B, C, D. Here again A, B, C, D. In third one also A, B, C, D. And fourth one is also again A, B, C, D. Therefore, these four permutations are same. But in case of linear arrangement, these four permutations, that is A, B, C, D, B, A, B, C, C, D, A, B, and B, C, D, A are different. In linear permutations, these are different, but in circular permutation, these things are same. Therefore, thus the circular permutations are different only when the relative order of the objects is changed. Otherwise, they are same. If we change the relative position, that is, if we take this B in between A and C on this side, and D, and replace this B and D, then this permutation is different. Otherwise, it will be same. Okay. Therefore, as the number of circular permutations are nothing but the relative position of objects. Therefore, as the number of circular permutations depend on the relative position of objects, therefore the number of permutation of these n objects in a circle can be found by keeping one element fixed and arranging remaining n minus 1 elements, which can be done in n minus 1 factorial way. Therefore here we have to fix one element. That is, if suppose we have fixed the a element, that is element A has been fixed, then we have to we have to permute or arrange these remaining three elements, and these three elements can be arranged by definition of permutation. These three things can be arranged in 3 factorial ways. Okay. Therefore, if we take n things and take one element as a fixed, then the remaining n minus 1 elements can be done in n minus 1 factorial. Therefore, the number of circular arrangement of n different things is nothing but the n minus 1 factorial. Here we have to just keep one element fixed, and we have to permute or arrange the remaining n minus 1 element, and which can be done in n minus 1 factorial ways. Therefore, the number of circular arrangements of n different things is nothing but the n minus 1 factorial. Let us see the example depending on this point. In how many ways can a party of 4 boys and 4 girls be seated at a circular table so that no two boys are adjacent? Okay. Solution. Four girls can be seated at a circular table in 3 factorial ways, which is from the above point. Since if we take the circular arrangement of four things, then we have to keep one element as a fixed, and the remaining three elements can be permuted among themselves in n minus 1 factorial ways. As here there are four girls, then we have to keep one girl fixed, and we have to permute remaining three girls, and which can be done in 3 factorial ways. Now, when they have been seated in their remain four places, for the boys, each between two girls. Now we have to take one boys at between two girls. Therefore, the boys can sit in 4 factorial ways. As there are 4 boys, then these 4 boys can be permitted among themselves in 4 factorial ways. Therefore, thus by the product rule, there are 3 factorial into 4 factorial, which is nothing but the 144 ways of sitting in the part. Okay. Now the next definition is nothing but, or next point is nothing but the clockwise and counterclockwise permutation. There are two types of circular permutation. First one is a clockwise and second one is a counterclockwise. Let us see what is a count. Let us see first one, that is those permutations in which clockwise and anti-clockwise arrangements are distinguishable. Thus, while sitting three persons ABC around a table, if we take one table and there are three persons A, B, and C, and now we have to see the permutation among these three persons, and we have to see the following permutations are the different permutation. In first one, there is an anti-clockwise permutation, which is A to B, B to C, and in second one there is a clockwise permutation, that is anti-clockwise means nothing but counterclockwise, and in second one there is a clockwise A to B, B to C. Okay, here the direction is different. Now, in second one, we have to see when clockwise and anti-clockwise permutations are not different. In first one, we have to see the clockwise and anti-clockwise permutations are different. In second one, we have to see the clockwise and anti-clockwise permutations are nothing but same one. Okay. ABC or ABC, both are the same. When clockwise and anti-clockwise arrangements are not different, that is, both are same, then the arrangements of beads in a necklace. Okay, beads is nothing but, that is the money in necklace. That is, we have to take beads in a necklace, arrangement of flowers in a garland. That is, we have to take the flowers in garland. Garland is nothing but the mala. Okay, that is, therefore the number of circular arrangement of n different things, as there is no difference between clockwise and anti-clockwise arrangement, therefore the number of permutation of these n things are nothing but the 1 upon 2 into n minus 1 factorial. As they are circular arrangement, therefore they can be arranged in n minus 1 factorial ways. But here the clockwise and anti-clockwise permutations are same, therefore we have to take any one belonging to that's why here we have to divide it by 2, and which is nothing but the 1 upon 2 into n minus 1 factorial. Let us see the example depending on this point. Now, in how many ways 8 different beads can be arranged to form a necklace? 8 different beads can be arranged in a circular form in 8 minus 1 factorial, which is equal to 7 factorial, which is from the definition of circular permutation. And as here there is no distinction between the clockwise and anti-clockwise arrangement, therefore the required number of arrangements is nothing but 1 upon 2 into 7 factorial. Since there is no difference between clockwise and anti-clockwise direction, either we can go from clockwise or anti-clockwise, then the result will be same. Hence, the number of arrangements are nothing but 1 upon 2 into 7 factorial. Okay, thank you for watching the lecture.